We mentioned in the last video that the concepts of the central limit theorem only apply in particular circumstances. And so now we want to take a look at what those circumstances are and what are the consequences of them. So up here we have the central limit theorem for means, and it says suppose there's a population of size capital N, which is an important thing to note. Capital N is the size of your population, not the size of your sample. So if you have a population of size capital N with mean, mu, and standard deviation sigma, actually I highlight that in green, and then mu was highlighted in yellow before and standard deviation sigma is in blue, then the sample size of n, little n, is selected such that the following conditions are met. These three conditions are going to come back several times in chapters 9, 10, 11, and so on. So this is not going to be a one-off. This is going to actually occur frequently and definitely beyond the exam as well as the final. So it says condition 1, random. Right, so everything has to be random, otherwise the rules of probability do not apply, and then we're not really in this class. Not random would mean it's biased. So that's what we're talking about right down here. So why is random so important? Well, it has to be random, the sample has to be random in order to protect against bias. There, I just typed that up. So if the sample is not random, then it will be biased, and all the conclusions we would draw and any mathematical operations we would perform would be invalid and worthless. We talk about that in section 1.5. If you haven't watched those videos yet, be sure you do, because that's a really important idea, that bias is a bad thing. Also, just all the formulas we're using, normal CDF, binom PDF, etc., they're all built on probability, like I was just saying, and that assumes randomness in order to be valid. So for those reasons, we would definitely need it to be random. All right, so now let's look at condition number 2. Condition number 1 is pretty easy, and quite frankly, we usually assume that we have it because we really can't do anything without it. So now let's look at condition 2, which is a much harder assumption to deal with. Namely that we need our samples to be independent, our observations to be independent. If the sample is collected without replacement, then the population must be at least 20 times larger than the sample size. In other words, little n must be, the sample size, little n, must be less than 0.05, which is 5%, of capital N, the population size. So let's think about this for just a second. We're actually saying we need a small sample. Well, not that small, but smaller than 5% if they're taken without replacement. So there's a couple things going on. One, if it's taken with replacement, then you have independent automatic. Independent, if it's with replacement, you automatically have. Let me type that up. Okay, so if the sample is taken with replacement, so think of all the things we did in chapters 5 and 6 that were with replacement, like dice and coins, things like that. So every time you pick it up, you know, all the numbers are back and possible, or both heads and tails are possible when you pick up a coin. That's with replacement, so you don't have to worry about that. In the case of surveys, it would be, so for example, people's names get drawn out of a hat, but then you put them back in and they're still eligible for being drawn, that kind of thing. I mean, it would be rare, but you could imagine there might be some circumstances where that could happen. If that's the case, then you automatically have independence and you don't have to worry about it. Where you have to worry is if it's taken without replacement. In that case, you really only want your sample to be less than 5% of the population. And the reason is because if you get more than 5%, people end up talking to each other. So for example, suppose I wanted to poll all JC students, but I have to call them all individually. When you hit a certain point, people know each other. If you get more than roughly 5% of the population, people will talk to each other and say, hey, Alana's going to call you about this. Maybe you should tell her that. And people will start campaigning for certain answers to certain questions if it's something that people care about. And so you'll lose independence because people will know that you're calling. So I always give the example in class of my dog. My dog goes in, we go into a pet store, and they always put the treat bins, the open treat bins, down at my dog's level. And I'll be sitting there looking at something, and then I'll feel this, and I'll look around, and I'll see my dog is very slowly and carefully pulling one treat out of the treat bin. Because, who's going to notice? If I just took one out of the whole bin, no one will ever know that I took it, right? it's the same idea. If you want to take a small enough sample, then no one will ever know that you did it, right? So that's my analogy for you. Um, so I just typed that up. So you want to sample a small enough, or you want to take a small enough sample that people don't talk to each other. Believe it or not, there are actually some cases of this happening where they got saturation of the surveyors and they ended up kind of calling too many people, and all the people would talk to each other at church and be like, oh, they're going to call, you better say this. And there's actually actual documented cases of that happening. As a matter of fact, to some surveys taking place in Michigan a few years ago. So you don't want to get that many people, right? So you want to be small enough that that just like a dog wants to steal a small amount of treats from a bin, you don't want to call so many people that everybody's going to know. So, so just like a dog wants to steal a small enough amount of treats from a bin that no one notices they're missing, a surveyor wants to call less than 5% of the population, or wants to poll a small amount of people so that they don't know that that the call is coming and, well, ruin the event or ruin the survey. Right, so it's a little esoteric, but it's an important concept, and it's going to come back a lot. So we kind of fake our way to independence, right? So when we're doing it with replacement, we don't have to fake it. It is independent. When you're doing it without replacement, you want to be less than 5% of the population. And again, think of it as like little kids trying to steal candy from a bin. You just don't want to steal so much candy that people notice, right? You don't want to call so many people and ask them questions that they're going to notice and start, ransacking what you're trying to do. And just for the record, we write this up and we talk about it, little n being less than capital or 0.05 capital N. When you do that, you're going to want to say what little n is and say what capital N is. Now, sometimes it'll be given to you in words or in numbers. I'll say, the population of Michigan is 9.9 million. So then use it. And if I don't tell you what it is, then you can kind of talk about it in words. Sometimes you can even Google it if it's like U.S. households or number of adult Americans. You can actually find that out on the internet, and feel free to if you want. But otherwise, we just kind of talk about it a bit. All right, so condition 3, normal. All right, so we do a lot of things based on the normal distribution. And actually, some of the other distributions we use are based on the fact that we had the population normally distributed to begin with. So there are 3 ways we can prove that. So we need it to be normal in one way or another. Now, for means, that can happen in 3 ways in terms of being given. When I say that, what that means is it'll actually be written for you in the problem somewhere. It'll say, and this was a normally distributed population, right in the instructions. Then that's given. Or I can give you a normal probability plot. That plot that we learned about in section 7.3, the shortest section in the course, right? So they'll just be drawn for you. You look at them, see whether the points are linear. If they're linear, then the distribution was normal. Now, if I don't give you either of these things, if I don't just write it in the instructions or give you that plot, the other thing I can do is give you a large enough sample size. So the sample size would have to be larger than 30 in order to ensure normality. So if I do one of those 3 things, then you have a normal distribution. Once you have a normal distribution, then we know by the central limit theorem that the distribution of the sample means. So think about it from last video, how x bar varies from sample to sample to sample, room to room to room. How do the averages vary across the rooms? Will create its own distribution that has a shape and a center and a spread. The shape of that distribution will be normal. And then let me just back up real quick. It'll be this little normal picture right there. Right? That normal curve will be what you have. So it will be normal and beautiful. It will have a center that is the mu, right? So there's a line going down the middle of that graph. That is your mu, that's your center. And it'll have a shape, or be a spread, which we talked about last time, that's smaller. And it's called the standard deviation of the sampling distribution of sample means. And that is just a lot to say. So they changed it to standard error. Right? The standard error, SE of x bar, is how the x bars vary from sample to sample to sample, right? Or expected to vary. Now, a lot of times we don't actually know full sigma because sigma is actually from the population. So we frequently use the approximation S divided by the square root of n.